I'm going to share my screen with you guys. Can you see my screen, guys?
Yes.
Okay, good. So last time we talked about this section 12.7. Very quick review. It talks about tangent planes, which we understand the tangent plane can be found out by using a more general format of function, right? We can find it from f of x, y, z. Also from tangent plane, we understand there's a line, so-called normal line. Normal line is the line that goes through, in the direction of the gradient. That's normal line. And then we started to talk about differential, okay? Differential is used for approximation. So it's different from increment, right? Increment is the exact change of the independent variables and dependent variables, while differential is the value that you compute from the derivatives. So differential, this is increment of z. Differential of z would be partial x times dx, differential of x, and plus partial y times differential of y. Okay. And we said that you can use differentials to approximate the increments when the change of x and change of y are small, relatively small, right? And then we did one question last time. That was example 6. Okay, example 6, you have a semicircle, right? Semisphere, and we use the differential to approximate the change of the z-score, the z value. So we have the last question here, example 7, using a differential as an approximation. I'll let you guys take a look at this question first of all, and then we'll think about how we can tackle this problem by using differentials. Okay, any thoughts? If it's a little bit kind of like abstract, you may try to sketch a graph.
Hey, Dr. Wu.
Yes.
Could the small incremental change be the copper sheet?
Yeah, the copper sheet, the thickness. You can first sketch a rough graph. Rough sketch of it. So it's used differential to find approximate amount of copper in the four sides and bottom of rectangular copper tank, right? Copper tank. So it's like a cubish, I mean, it's not exactly a cube, but it's rectangular tank, right? So you're using the copper to wrap it around, sort of. Right?
Mm-hmm.
So there's length, width, and depth, right? Length, width, and depth. It tells you that the length is 6 feet, and width is going to be 4 feet, and the depth is 3 feet. So inside it's going to be those measures. And then you're using the copper. These are the areas you're going to fill with the coppers, right? Filling with the coppers for those areas. Okay. And the copper is 1/4 inch thick. So first of all, there's a question of using inch and then using feet. You notice that there are different units, right?
Yeah.
Everybody notice that? Feet and inch. So first of all, let's convert feet into inches. Okay. So they would have a consistent unit. So for example, 6 feet is going to be how many inches? 1 feet is
12 inches.
Yeah, 12 inches, right? 1 feet is 12 inches. So length, which is 6 feet, that's 72 inches. Okay. And width, which is 4 feet, that's 48 inches. And depth, which is 3 feet, that's 36 inches. Okay. And then let's see the thickness of the copper. The thickness of the copper basically would increase the length, increase the width, and increase the depth in a certain way, right? So how much the length has been increased due to the copper? Think about the length. If you take a look at this whole rectangular tank from this side, okay, guys, think about your eyes are here. You're looking from this side. Inside is the original length, right? Now you have copper in the right and the copper in the left, right? So how much the length has increased? What's the increment of the length? This is 1/4 thickness of the copper. Yeah, 1/2. Here's also of 1/4 inch thick of the copper. So delta L here is going to be 2 of the 1/4, right? So 1/4 plus 1/4, which is 1/2 inch. Okay. So change of L, change of length is 1/2 inch. Okay. Similarly, can we get change of the width? So you're looking at this tank from the right side. Should that be the same kind of?
Yes.
Yeah, so it'll be 1/4 plus 1/4, which is 1/2 inch, right? What about the change of the depth? You can still look at it from the front view, right? From the front, then originally this is the depth, right? This is depth. And with the copper, be careful how it is phrased. The copper is only on the 4 sides and only at the bottom, right? Only at the bottom. So bottom, there's copper here, not on top. Make sense? So only 1/4 to the bottom, not on top. So delta D, the increment of the depth was only be 1/4 inch. Okay. Okay, is that clear so far?
Yes.
Okay, now let's see. So this is increment of L, this is increment of width, and the increment of the depth. Each of these increments compared to the original length, is that a small increment?
Yes.
So 1/2 inch compared to 17 inches. This is really a small increment of the length, right?
Mm-hmm.
Similarly, for the increment of the width, you are comparing 1/2 with 48 inches. So all of these are very small changes, right?
Mm-hmm.
If these are small, the change that with the thickness of the copper, is that affecting, I mean, what concept is that affecting? Are we talking about the volume? Are we talking about the area? Or are we talking about anything else?
The volume.
Yes, so volume, right? With the copper, it changes the basically volume, right? Delta V. Now, due to these small increments, and how do we calculate V, by the way? V of a rectangular tank. How do we calculate the V?
Base times height times.
Yeah, so the area of the base times the height, which is length times width times depth, right?
Mm-hmm.
Times width times depth. So with these coppers, the total volume is going to increase certain amount, and this is delta V. And because all of these small change of the independent variables, delta V could be approximated by using dV. Okay. So we can use differential of the volume to approximate the change of the volume, which is basically is the volume of the copper, right?
Mm-hmm.
Okay, so the question is just about what is the differential of V, right? Differential V. So V is the dependent variable. Independent variable are length, width, and depth. Okay? So we can just refer to our previous conclusion. It will be related to differential of length with partial V, partial L, right? And plus differential of the width multiplied by the partial derivative, partial V, partial W, and plus differential of the depth, sorry, it happens to be dd, and partial V, partial depth. Right?
Mm-hmm.
And each of these differentials, dl, is the same as delta L. So I can replace those by partial V, partial L times delta L plus partial V, partial W times delta W plus partial B, partial D times delta D. Okay? And keep going. We have partial V, partial L, partial derivative volume with respect to length. What is that? Folks, what's partial V, partial L? So you're treating length as the variable, right?
Mm-hmm.
And W and D are just constant coefficients. So the derivative will just be
0? No.
This will be 1, right? 1 times WD, right? So just be WD. Make sense?
Okay.
Because the derivative of length with respect to the length will just be 1, right?
Mm-hmm.
1 times WD. So WD times delta L plus partial V, partial W. Partial V, partial W. Same thing. LD, right? Length times depth times delta W. Partial V, partial D. Partial V, partial D will be length times width times delta D. Okay, and then in the end, let's just plug in every value we have. So the width is 48. The depth is 36 inches. Delta L, change of the length is 1/2. And length is 72. Depth is 36. change of the width is 1/2 as well. Keep going. Length is 72. Width is 48. And change of the depth is 1/4. So you calculate this amount, you add it up, that's gonna be the change of the volume of this tank, which is the volume of the copper that will be used. Right? The unit should be, what's gonna be the unit of our calculation?
Inches cubed.
Yep, inches cubed. Okay, any question about this problem? I can review what we just did again. Okay, first of all, we can sketch a graph based on what you see here. So we sketch a tank, and we understand in the outside of the tank, you are filling in with the copper, right? The four sides and then the bottom. So basically what we are evaluating change of the volume of the tank, which is the volume of the copper. And we can write down the length, width, and depth based on what is given and change them to the unit inches. And we look at the copper, which is 1/4 inches thick. So with the copper, it's gonna increase your length, okay, increase your length by 2 sides. So 1/4, that's 1/2. By using these copper, it's also going to increase the width by the same amount, 1/4 plus 1/4 is 1/2. It's gonna increase the total depth only by 1/4 in the bottom, right? 1/4 inch. So these are the increment of the length, width, and depth. Now, because the volume is calculated by length times width times height, which is length times width times depth here, and each of these increment L, W, and D are relatively small, very small. So the change of the volume could be approximated by differential of the volume. Therefore, we'll just use the formula, right? Differential volume will be differential of the length times its partial derivative, and differential of the width times its partial derivative, and times differential of the depth times its partial derivative. And then just plug in the corresponding numbers. Okay? Any questions with this problem? And it's relatively easy to compute, right? You can see 36 1/2 could be reduced, and 36 1/2 could be reduced, and 48 times 1/4 could be reduced. So it should be a pretty easy computation over here. Okay, so this is one example of using differential as approximations in applications. Okay. All right, so that finishes our section 12.7. Let me get out of this here, and we're gonna go to the next section today, which is section 12.8. Can you guys see my screen?
Yes.
Okay, because sometimes the share screen would stop for no reason. So this is next section 12.8, which talks about extremas, okay, extrema. So maxima and a minima. Do these sound familiar from Calculus 1, maxima and a minima?
Yes.
Right? So it's the maximum value and a minimum value of the function. What we're doing here is we want to find two extremas, two kinds of extrema. One is called absolute extrema, or also called a global extrema. And the other one is called relative extrema, Some book also call it as local extrema. Okay, so these are different verses you may see. We are focusing this time on a function of two variables, right? Two variables. We also will introduce a test which is so-called second partial test. Okay, second partial test is used to find relative extrema. It's used to determine whether this is a relative max or relative min of a function of two variables. So these are the two tasks we want to do today. First of all, concept-wise, let's try to be able to identify what is absolute extrema, what is relative extrema, okay? Or what is global extrema, what is local extrema. So let's take a look at this graph. This is a graph from z equals f of xy. It's a function of two variables. We understand that should be a three-dimensional, right? 3D surface. Surface. Surface, and this is suppose is its domain. Okay, suppose this is the domain. This domain is a closed bounded region R. Okay, closed bounded region R. So it contains all the boundary points as we talked about before. And this is the part of the surface that corresponds to this domain. Okay, this domain. So it's easy to just look for the maximum and the minimum, right? So the maximum are the highest point when you're looking at a z value. The highest will be maximum and the lowest will be minimal, right? Minimal. So the definition is the values of f of AB and FCD, f of AB, such that f of AB is smaller than any other function value. Therefore, this will be the min. And FCD is higher than any other values. So this will be the max. Okay. Again, this is referring to the function values, so the z values. Right? Function value. So the z values. So it's the highest z value, this is the highest z value, and this is the lowest z value, right? And this is pretty straightforward when you look at the maximum over the entire domain. So this is also called the global or the absolute max, absolute min. Okay. And over here we talked about, let's kind of refer back to what we mentioned before. A region is closed when it contains all of its boundary points. Okay. We need to understand this because later on, when you're looking for extremas, you need to pay attention to the corresponding domain, whether it's closed or open. Okay. The extreme value theorem deals with a region in the plane that is both closed and bounded. And that refers to another concept. What's bounded? So a region in the plane that is called bounded when it is a subregion of a closed disk in the plane. Okay, subregion of a closed disk. And a lot of the times these would be able, you can tell these information from the question itself. So next theorem talks about extreme value theorem. This basically talks about the existence of maximum. Okay. It guarantees when would the function have minimum, when would the function have a maximum. Okay. I'll give you guys 1 minute to read the theorem real quick. Can you identify the keywords that would guarantee the existence of a minimum and a max and a maximum?
Bounded.
Okay, the region, right? The region needs to be closed bounded, okay, first of all. Secondly, function f, there are certain requirements for function f itself, right? Function f needs to be a continuous function. Okay. Continuous function means there's no jump, there's no hole, right? It's a continuous function. So with the existence of these two conditions, function being continuous and it is on a closed boundary region, then the minimum value and a maximum value must exist. Okay. So this theorem basically talks about the existence of extreme. The function must have a minimum or maximum if it's continuous on a closed bounded region. Now going back to this graph, you can tell this is a continuous function, right? Continuous function, and it is on a closed bounded region. Therefore, it must have a max, it must have a min. All right, so keep going. This one just kind of try to define what is relative extrema. Okay, relative extrema. We just talked about absolute min and absolute max, which is absolute extrema. Next, we want to talk about relative extrema. Okay. So relative extrema is an idea that's opposite to absolute extrema. Okay. So the function f has a relative minimum if the function value will be greater than that function value in an open disk containing the point. The function f has a relative max if this is sort of a higher value than any other function value in an open disk. So this time you can tell it is not closed, right? This is open this time. So we're not looking at a closed region, we're looking at an open region, okay? A small open region. This is closed and there is a small open region. Okay. So the function value over this small region will be relatively, whether it's relative max or relative min. The other easy way to understand the relative extrema is just those highs and lows in a small area. Okay, small area. Now, folks, if you look at this graph, can you sort of tell there is an absolute max?
Yes.
It would be absolute max, right? But can you tell there are some relative maxes? Yeah, like these relatively high ones, okay, in their small region, including this, right? So all of these would be relative max. So you may have multiple relative max, but there should be only one absolute max, right? So that's the difference between relative extrema and absolute extrema. I think we discussed this in Calculus 1 as well, so this shouldn't be a new concept to you. Relative extrema is just in a small area, while the absolute extrema is over the entire domain, right? And next, the question is, how do we find the relative extrema? Relative extrema. So where would those relative extrema simply occur? And you probably recall this concept of those critical points. Okay, critical points. The relative extrema would occur at those critical points, right? Critical points. There are two types of critical points. One is called stationary point. One is called singular point. Okay. I'll let you guys take a look at the definition of this critical points. Does this kind of like bring back your memory in Calculus 1 of the critical points? Right, okay, I can do a quick comparison. In Cal 1, y equals f of x. Here is in Cal 3, z equals f of xy. Okay, in Calculus 1, critical points. Here, critical points. Calculus 1, you only have a function of one variable, so it could be like this, right? and over a closed region, okay, A, B. Then the critical points basically is referring to these points, right? These points, which is derivative, I mean, f prime of x equals 0, right? Derivative equals 0, or sometimes derivative does not exist. Those two types. This is stationary point. This is called singular point, right?
Mm-hmm.
So similarly, in calculus 3, when we have a function of two variables, we can also have similar types. The first type will be first order derivative. So partial x equals 0, partial y equals 0. Those are the stationary point, like here. And when the derivative does not exist, so that's saying partial x doesn't exist, or partial y doesn't exist. These are the singular points. Okay, singular points. So you're just carrying out our old knowledge in calculus 1 and extend that to calculus 3. Okay. Stationary point remains and singular point remains as critical points. Okay. Put that into the graph. When we're looking at the stationary point, stationary point, due to the gradient being 0, right? Due to the gradient 0, that means the tangent plane has to be horizontal on that specific point, right? On this point. If you guys look at these two graphs, okay, you can tell that on these two graphs, the tangent plane, they are both horizontal, right?
Mm-hmm.
Is there something special about these 2 points? How are they special? I mean, are they related to some extreme values?
Yes.
Like this one, right? F of x0, y0, you can tell it's the highest point, is the max, right? In this graph over here, f of x0, y0, it is the lowest point, is a min, right? So the horizontal tangent plane, the corresponding point, will give you either some max or min. Okay. Okay, so the next theorem just says relative extrema occur only at critical points. Okay. So if function f has a relative extrema at the point, okay, on any open region R, then the point has to be a critical point, which means has to be either stationary or singular, okay, which is both related to the gradient of function f, right? So partial x and partial y. So that means if you are looking for relative extrema, we'll just need to pay attention to the gradient of function f. Okay. Any questions so far?
No.
Okay. So let's start with the next question, example 1. Finding a relative extrema. Determine the relative extrema of this function f of xy, 2x squared plus y squared plus 8x minus 6y plus 20. Notice that we didn't say xy has to be in a certain region, right? So xy could be r times r. So it could be any real number times any real number, which is an open region, right? Open region. Any thoughts? What should we be looking at?
The partial derivative of x and y.
So that would be the gradient of function f, which is partial x and partial y. We should investigate these two. Partial x would be pretty easy to find, which is 4x plus 8. Good. Partial y would be 2y minus 6. Okay. Okay, so the gradient, okay, is 4x plus 8, 2y minus 6. This one always exists, right?
Mm-hmm.
Which tells us is there any singular point?
No.
Yeah, singular point is where the gradient does not exist. So it always exists. There's no singular point. Okay.
So I have a question, Dr. Wu.
Yes.
So if that vector were to have a restriction,
Mm-hmm.
then it's likely that it would have a singular point.
Yeah, for example, if we have 4x plus 8 divided by x minus 1, right? If you
Yeah.
have dividing by something, then you know sometimes it won't exist.
Okay.
Then singular point would exist. Mm-hmm.
Yeah,
Then there would be a singular point. Mm-hmm.
Mhm.
We should be looking at a singular point. But since in this question there's no singular point, and so the only types of critical point will just be stationary point, right?
Mm-hmm.
So we can only look at a stationary point, which is when partial x is equal 0 and partial y equals 0. Pretty easy to do. So let's set partial x equals 0 and set partial y equals 0 at the same time. So that gets you x equals to -2 and y equals to 3. So that's -2 and 3. So there's the point -2, 3. Okay, so now the question is, we understand this point is going to be a stationary point, right? Which means it will have a horizontal tangent plane. Like what we did there before, like here, horizontal tangent plane. But whether it's the relative max or relative min is still unknown, right? Whether it's on top or on bottom. So how do we do that? Let's first of all check its function value. So f of -3, -2, 3. Let's first calculate its function value. The function value, let's just plug in -2 and 3. So we have 2 times -2 squared, which is 4, plus 3 squared, which is 9, and plus 8 times -2, which is -16, and minus 6 times 3, which is 18, plus 20. Okay. So we have 8 plus 7, my bad. So 8 plus 9, which is 17, minus 16, which is 1. 1 minus 18, that's -17. And then plus 20, that is 3, right?
Mm-hmm.
The function value. Question is this a max or min? Right?
Mm-hmm.
Any thoughts? How do we determine whether this is a max or min? Relative max or relative min?
Second derivative test, second partial.
Second partial, but we haven't introduced that yet. But
okay.
without that test, any other thoughts? You can determine whether it's max or min, whether it's the point on the top or whether it's the point in the bottom. Any thoughts? Can we find some point just next to it and then compare their function value, whether it's bigger or smaller? Right?
Yeah.
Okay. So I'm going to find other points. Okay, find other points, which is not -2, 3. So suppose I'm finding 0. Wait, let's find some point which is close to it. So you can find -1, 2. -1, 2. So these two points are not far away, right? Not far away. Let's figure out what is the function value at -1, 2. Give you guys a minute to calculate this amount. I'm going to do it over here because I'm running out of space there. What do you guys get? What's the value at negative 1, 2?
Mm.
Folks?
Would it be 6?
Yep. Is that what the other folks got, you guys? Yep, so f of negative 1, 2 would be 6, right? If you pick a point that's close to negative 3, you get function value being 6. So that means 3 is going to be a max or min. 3 is apparently smaller than 6, right?
Mm-hmm.
Our value is smaller than any other function value, so this should be a relative min. Makes sense? Is that clear?
Yeah.
Our function value is lower than any other function value, therefore this function value would be a relative min, right?
Mm-hmm.
Okay. Let's we can write a summary here. We can say therefore function f of xy has a relative min. Back here. Relative min, minimum value of 3. Oops. Oh, what happened? Okay. Relative min of, let me get my pen initiated. Relative min of 3 at the point negative 2, 3. Why is this showing over there? Please move the moon away from the shared screen application. Do you guys see this box on my screen?
Yes.
Oh, okay. So it looks like it's disappearing. Okay. It's annoying here. I'm trying to move you away. Oh, let's forget about it. So, I've attached the solution here. First of all, we find a partial x and partial y. And you set both of them equal to 0, you get negative 2, 3. You can compare this value with other value, that's easier. And the other way you can do it is completing the perfect square, but this is probably a little bit tricky, okay? But anyway, the conclusion is we find a relative min, a function, relative minimum, which occurs at negative 2, 3, okay? The conclusion is consistent with what we had over here. So the function has a relative minimum value of 3 at negative 2, 3. Okay. So this is the graph, right? So the surface is looking like this, kind of like a small bowl. And then the point that we figure out is negative 2, 3, which is over here. This is the point. And by looking at the graph, you can confirm that this point does give us the relative min, right? It's not only relative min, it's actually the absolute min in this case, right? Mm-hmm. So it is both relative extrema and absolute extrema. So, so the question is, the next part is second partials test. What this test is used to do is whether it's to determine whether the critical points gives whether a relative max or min value. So by using this test, you can figure out immediately whether that function value is max or min. Okay. We actually had in calculus 1, if you guys recall, we had a second derivative test. Anybody recall second derivative test?
Yes.
It was used for concavity, right? Which means basically when I taught my students, I use this symbol here. So if the second derivative, I mean, if we're looking at the stationary point, which is here, right? Stationary point, meaning it has horizontal tangent line. If the second derivative, okay, if the second derivative is actually positive, then it's concave up, right? Concave up, then you know the point is going to give you a relative min, okay, the relative min. So second derivative positive, you get a relative min. When the second derivative is negative, then the graph looks like this. It gives you a relative max. Okay. You can use second derivative to tell immediately whether it will give you a relative max or relative min. And the same idea applies here for a function of two variables. We call it second partials test. Yes, second partials test, because we have partial derivatives involved now. Okay, let me see how to get this. Please move this window. Wait, there's no window I can move it. So annoying. Okay, I'll give you guys a minute to read the slide. Okay, so the second partial test not only tells you whether it gives you a relative max or min, okay, max or min. When we have a function of two variables, we actually have another concept, so-called saddle point. Okay, saddle point is the one that does not give you, it provides you neither, okay, so neither max or min. It's a kind of weird point. So it's neither max nor min at saddle point. Okay. Let's look at one example here. So this is a graph of the surface of y squared minus x squared. Okay, you can generate those from any computer system. So this is a function, and can you tell there's one point that might have a horizontal tangent plane?
Yes.
Right, so if you look at, yeah, right here, it should have a horizontal tangent plane, which means this is a stationary point. Right, stationary point. However, if you look at the function value, but f of 0, 0, right, the function value, which is 0, okay. 0 obviously is not the max, is not relative max. 0 is also not a relative min, right?
Mm-hmm.
Or relative. So it doesn't give you extreme values at all, even though it is a stationary point. So this point is called saddle point. And you can also tell this name by sort of try to like imagine a saddle, right? This does look like a saddle. The point is right in the middle of the saddle. So saddle point doesn't give you any extreme value, even though it is a stationary point, okay? Mm-hmm. So this is one concept that's new for a function of two variables. So the next slide just explains what we just discussed. The point 0, 0 is a saddle point. It doesn't give you relative max or relative min. Okay. Now let's look at the actual second partials test. Okay, first of all, give you 1 minute to read this test, and then we'll decompose it into 2 parts. Okay, first of all, the second partials test start with the stationary point. So it only works for stationary point. Okay. Secondly, when you are trying to perform the second partials test, you have to construct a D. Okay. D is made up by all the second partials, right? Could be fxx, fyy, and subtract the mixed second partial, fxy squared. So basically, it's fxx times fyy minus fxy times fxy. So all the 4 types of second partials all combined. Okay, that is the D. And there are 3 ways of D that you can see. If D is greater than 0, then this one would give you relative extrema. If D is less than 0, then the point is actually a saddle point, meaning neither max nor min, right? Mm-hmm. If D equals 0, then the test is inconclusive. There's no conclusion you can draw by doing the second partial test. We don't see this item 4 quite much. Usually it's going to be item 1, 2, or 3. Okay. So basically, if D is greater than 0, then you can determine whether it's relative max or relative min. Okay. So the next item you should be looking at will be looking at fx. Okay. Second partial derivative with respect to x. It's only about x here. If the second order derivative with respect to x is greater than 0, then function has relative min. If the second order derivative of x is less than 0, then the function f has a relative max. Now, once again, this is kind of like similar to what you did in calculus 1. Okay. Second partial derivative being positive, you get a relative min. Second partial derivative of x being negative, you get a relative max. See that? Mm-hmm. Right? Okay. So you can recall this. You can also relate this with your calculus 1 conclusion. But this is all built upon the conclusion your D needs to be greater than 0, first of all. Okay. So the idea is, if you do a flow chart, first of all, you calculate the D, right? Now, if D is greater than 0, then you go ahead, check fx. If fx is greater than 0, then it's relative max. Relative min, my bad, relative min, this graph. If fxx is less than 0, then it's relative max, okay? Let's apply this question to the next problem here. Find the relative extrema of function f of xy equals negative x cubed plus 4xy minus 2y squared plus 1. Okay, what do we do first of all?
Find a partial.
Yes, first of all, let's find stationary point, right? which is also the critical point here. Okay. So partial x and partial y. Partial x would be negative 3x squared plus 4y. Partial y would be 4x minus 4y, right? Okay, set both of them equal to 0. Okay, this is a system of equation, okay, with two unknowns, x and y. So I'm going to call this equation 1. I'm going to call this equation 2. Okay, any thoughts? How can we solve this system of equation?
Substitution? No, wait.
You can do substitution, absolutely. From equation 2, looks
Or
like,
you could
or you can do elimination method, right? Just by adding these two equations. Either one would be fine. If you like to do substitution method, then equation 2 will give us x minus y equals 0, meaning x is the same as y. So we can plug this in through equation 1. So we would have negative 3x squared plus 4 times x would be 0, right? Okay, we can factor out x, and you would have negative 3x plus 4 equals 0. So that means x equals 0 or x equals to 4/3. Is that correct?
Yeah.
Okay. Once you got x, do we know why?
Yes.
Because y is the same as x, right? So when x equals 0, y would be 0. When x is 4/3, y would be 4/3. 4/3. So there are two critical points, right? One is 0, 0. Okay. First point is 0, 0 at the origin. And the other point is 4/3. 4/3. Okay. But again, the question arises whether this will give you a relative max or a relative min needs to be determined. So next we do second partials test. Okay, second partial test. So this is the step 1. This is the step 2, right? Step 2. Step 1, step 2. Use second partials test. Okay. So first of all, you need to get the d. D is fx times fyy minus fxy squared. Let's see, what is fxx?
Negative 6x.
Yeah, we have fx. Yeah, question?
Is x?
Yeah, negative 6x, because we have fx being negative 3x squared. So second will be negative 6x. Fyy would be negative 4, right? Minus fxy. So fx take derivative with respect to y would be 4. You guys okay? Squared, right? So that is 24x minus 16, right?
Mm-hmm.
Okay, so this is the d, okay? And fx here, and fxx is negative 6x, right? So we're going to use the second partials test for these 2 points. For point 0, 0, we're going to use it to test this point. We're also going to use the second partials test to test the point 4/3, 4/3. Okay. So let's see. So first of all, for the point 0, 0, okay. D at 0, 0. Okay, so D at this point 0, 0. What do we have?
Negative 16.
Negative 16. Okay, this is actually a negative number, right? What does that tell us?
It's the saddle point.
Yes, so 0, 0 is a saddle point. Okay, saddle point, which means function at 0, 0 is neither max nor min. Make sense?
Yep.
Okay, second, let's test the point. The other point that we have, 4/3, 4/3. 4/3, 4/3. Hopefully we can get some useful conclusion here. So the D at 4/3 is, so if you plug 4/3 in, I have 24 times 4/3 minus 16. 3 and 24 could be reduced as 8. So 8 times 4, 32, minus 16, which is 16. Okay, good. Guys, are you still with me?
Yes, and something happened.
The screen is not, you don't have the screen? Yeah, let me see. Okay, do you have it now?
Yes, I see it now.
Okay, yeah. Sorry about that. I don't know what's going on there. Okay, it says the internet connection is not stable. Here, let's see. All right. Okay, let's still going back to here, right? Do you see my screen now?
Yes, it just shows maximum and minimum. The first page of the PowerPoint.
Oh, really? Okay.
Yeah.
Let me share the screen here. So, resume share. New share, and share the screen. Share the screen. Okay, is that back to where we left?
Yes.
Okay, good. Let's just finish this question and then we're done today, okay?
Okay.
All right, so let me put my pen back here. So we're at here, we figure out the D is actually greater than 0, which is good news, right? Because we know if D is greater than 0, then it will definitely give us a max or min. Next, we should check fxx, right? So fxx is -6 times x. The x would be the x value at this point, which is 4/3. Okay. So apparently this is going to be negative, right?
Mm-hmm.
All right, so if it's negative, you can use this graph again, and it's a crying face. Okay, crying face. Second derivative being less than 0, that tells us this is going to be a relative what?
Max.
Yes. Okay, so your conclusion would be, so function f of xy has a relative max at the point 4/3, 4/3. Okay. And you can also compute its actual value. Okay. You can also compute what exactly this max value is. I think I included that into my slide next. You guys can still see the screen, right?
Yes.
Okay, so if I put everything into the solution, then once again, you first of all find the critical points. These we all have done it. Okay, partial x, partial y. Second, both equal 0. Solve for x and y. So you got 2 points. And then find all the second partial derivatives and find the d. We've already concluded 0, 0, at 0, 0, there is a saddle point. Okay. And we looked at the 4/3, 4/3. We looked at the D, and we figure out the D is positive, okay? And second order derivative is negative. Therefore, it's going to be a relative max. And you can see this from the graph, okay? This is the graph here.
Mm-hmm.
This is a 0, 0, which is indeed a saddle point. It's in the middle of the saddle, right? Saddle point. And the 4/3, 4/3 is here, okay? It gives you a relative max. Okay, based
Hey, Dr.
on
Wu.
and partial test. Yes.
I have a question. So why did you use fxx and not fyy?
Yeah, that is an interesting question. I don't know. I think this is just more related to goes back to the calculus one. This fx is just like f double prime.
Okay.
Right? You can just do an like analogy of second derivative f double prime. Okay. So f double prime, second derivative test, right?
So we should always use fxx.
Correct. You always use fxx.
Okay.
Yep. So the graph is pretty self-explaining right here, right? It's a relative max at this 4/3, 4/3. Okay, let's stop right here, guys. Next time we're gonna do one question of the absolute extrema, which is a little bit more complicated. Okay, any other questions, folks? Is everything fine? Let me check with my other participants. Mary, Victor. Oh, they don't have they've muted themselves. Okay, so I think we can just stop at here, guys. How is it, guys?
That's good.
Okay, I'm gonna see you guys next Monday. I'll post homework on my courses as well. Okay, thank you.
Bye, Dr. Wu.
Bye-bye. Yes. Let's see. Thank you, Victor. So I'm gonna end meeting.